Up until this point, the tests of inferential statistical analysis that we have discussed have all focused on comparing groups and using data that either was continuous or rankable. Statistical analysis to compare groups allows us to determine if there are significant differences between the means or distributions of two or more groups. Statistical tests that compare groups generally answer questions about how is A different from B. Sometimes the questions that investigators need to answer are not questions about the difference between groups, but rather questions of association or correlation, questions that ask how is A related to B. We briefly touched on the topic of correlation during our first lecture of this series when we talked about accepting and rejecting null hypotheses, and then again when we talked about effect size. If you recall, we discussed how Pearson's R is a measure of effect size that helps us understand the strength of the relationship between two variables. Pearson's R, however, is only valid for data measured at the interval or ratio level. Yet, there are important variables that can only be measured at the nominal or ordinal level and thus do not lend themselves to arithmetic analysis. In this lecture, we are going to be discussing non-parametric tests that can be used if we want to understand the relationship between two or more categorical variables, including variables at the nominal level of measurement. We will discuss when and how to apply three different non-parametric tests of association: the chi-square test, Fisher's exact, and McNemar's test, as well as explain how to calculate effect size for these tests using either phi or Cramer's V. At the end of this lecture, students should be able to explain what is meant by crosstab analysis and contingency tables. Students should be able to discuss when to use each of the two measures of effect size for categorical non-parametric tests of association, be able to distinguish between when to use each of the three non-parametric tests discussed, list the assumptions for each non-parametric test discussed, and describe what results to report for each non-parametric test discussed. Categorical level variables can be examined visually using frequency tables, as we discussed in our lecture on displaying data visually. Frequency tables allow us to visualize the frequency of different occurrences or outcomes for one variable. For example, a frequency table could be used to determine the number of nurses on a unit who have associate's, bachelor's, master's, and doctorate degrees. A limit of frequency tables is that they only allow us to obtain information about one variable. Thus, analyzing frequency tables does not help us answer the more sophisticated questions about the relationship between two or more categorical variables. To better understand the relationship between two or more categorical variables, we can build a contingency table to visually represent the frequency of occurrences based on the interaction of multiple variables. In other words, a contingency table would allow us to analyze joint frequencies, as contingency tables provide data on how many occurrences fit into two or more given categories, such as not only how many nurses on a given unit have a bachelor's degree, but how many nurses in the ER have a bachelor's, how many nurses in the ICU have a bachelor's, and how many nurses on the med-surg unit have a bachelor's. Analyzing these joint frequencies is referred to as crosstab analysis. To help you better understand this concept, we will look at an example on the next slide. Crosstab analysis is an extension of frequency analysis that allows you to move from looking at just one variable to looking at multiple variables. Say you are a nurse investigator and you collect data on the highest education level of nurses working in the ER. You would be limited to analyzing this data using a frequency table where you would calculate what percentage of nurses have an associate's, bachelor's, master's, and doctorate. You then decide you want to find out if there is a correlation between the highest level of education and the unit that nurses work on. Therefore, you collect data from the ICU and the med-surg unit as well. We're going to pretend this is a very small hospital for our example. You can now perform crosstab analysis to see if there is possibly an association between level of education and unit the nurses work on. You can build a contingency table to visualize this data, as I have done on the slide. Contingency tables can compare two or more variables and are verbally referred to as size A by B, or A by B by C, for up to how many different variables you are comparing. The first number is the number of categories for your first variable, the second number, the number of categories for the second variable, and so on. Thus, the table on the slide comparing level of education, which we have 4 categories for, to the hospital department, which we have 3 categories for, would be a 4 by 3 contingency table. You can also see we include totals in a contingency table so that you can easily calculate how many nurses work on each unit and how many nurses have each level of degree. Both of these numbers should add up to the same total of 20 nurses, which they do. Crosstab analysis is the foundation upon which statistical analysis of categorical level data is built. On the next slide, we will briefly review measures of effect size for non-parametric tests of association, which will help us understand how strong the relationship between the variables is. As we have discussed multiple times, effect size is an important calculation when performing inferential statistical analysis. Tests of statistical analysis help us determine if a relationship is likely a true relationship or the result of chance. However, without a measure of effect size, we don't know how strong a relationship is, only that the likelihood is the relationship is not by chance. On the upcoming slides, we're going to discuss 3 statistical tests to analyze association between categorical variables: the chi-square test, the Fisher's exact test, and McNemar's test. When we report our findings from these tests, further clarity is provided when we include a measure of effect size. Phi is the measure of effect size that should be used for Fisher's exact tests, McNemar's tests, and chi-square tests that are dichotomous, or 2 by 2. What that means is that both variables have only 2 output options. Usually, these options are yes or no, present or not present. Phi is denoted by the Greek letter phi. The measurement for phi ranges from -1 to +1. The closer to -1 phi is, the stronger the inverse relationship is, and the closer to +1, the stronger the positive relationship is. A small effect size is an effect size around between -0.3 and +0.3. A moderate effect size is between -0.5 and -0.3, or +0.5 and +0.3. And a large effect size is smaller than -0.5 or larger than +0.5. Cramer's V should be used for chi-square tests that are not dichotomous, or in other words, when at least one of the categorical variables has more than 2 categories, such as our example with the relationship between level of nursing education and unit that the nurses work on. Cramer's V is denoted by the letter V. The measurement for Cramer's V ranges from 0 to 1, and the closer Cramer's V is to 1, the stronger the relationship between the variables. A small effect size for Cramer's V is less than 0.3. A moderate effect size is between 0.3 and 0.5, and a large effect size is greater than 0.5. The formulas for computing phi and Cramer's V are beyond the scope of this class. However, when you run a chi-square test, you will get the effect size for both phi and Cramer's V. Thus, it is important that you clearly understand which one to choose to report so that your data reporting is accurate for effect size. We are now ready to begin looking at non-parametric tests for categorical data. The chi-square test is the simplest method to analyze variables that are measured at the categorical level. The chi-square test can be used to answer questions about the relationship or association between at least 2 variables. While chi-square can be used to test the relationship amongst more than 2 variables, you will rarely see this done in practice. Since the chi-square test is a non-parametric test, this means it does not require an assumption of normal distribution. However, similar to non-parametric tests for comparing groups, the chi-square test does have a set of assumptions that must be checked. First, all observations must be independent. Second, the expected count or cases in each cell should be greater than 1. And third, the expected count or cases in no more than 20% of cells should be less than 5. If you look back at my example, for the nurses, you can quickly confirm that we could not use a chi-square test to analyze this data, as the count for most of the cells is less than 5, and multiple cells include a count of 0. For a chi-square test, the null hypothesis would generally look like there is no association between the two variables, and the alternate hypothesis would look like there is an association between the two variables. As with all tests of analysis, you would use software such as Microsoft Excel or IBM SPSS to compute the test statistic and associated p-value. If the p-value is smaller than your chosen alpha level of significance, you will reject the null hypothesis and say that there is an association between the two categorical variables. If the p-value is larger than the alpha, we will accept the null hypothesis and say there is no association between the two categorical variables. To report your analysis using a chi-square test, you would include the chi-square statistic with its associated degrees of freedom and the p-value. Your statistical software will provide degrees of freedom, but in case you are interested, the formula for degrees of freedom is number of rows minus 1 times number of columns minus 1. You should also report the appropriate measure of effect size. If the contingency table is 2 by 2, report the value of phi. If either or both variables include more than 2 categories, report the value of Cramer's V. The chi-square test has 2 assumptions related to count. First, the count for each cell needs to be greater than 1, and second, no more than 20% of cells should have a count less than 5. If either of these assumptions are violated, the chi-square test becomes unstable. In other words, the chi-square test no longer is a valid and reliable tool for analysis. Thus, the famous statistician Fisher developed the Fisher's exact test in 1922 to address this limitation of the chi-square test. The Fisher's exact test has the following assumptions that must be checked. All observations must be independent. The contingency table must be exactly 2 by 2, meaning comparing 2 categorical variables where each variable has exactly 2 categories. The sample size is small enough that the assumption of the chi-square test are violated. Similar to a chi-square test, the null hypothesis for a Fisher's exact test would generally look like there is no association between the 2 categorical variables, and the alternate hypothesis would generally look like there is an association between the 2 categorical variables. As with all tests of analysis, you will use software such as Microsoft Excel or IBM SPSS to perform a Fisher's exact test. However, this test is slightly different from all the other statistical tests we have discussed thus far. To this point, our software has provided its test statistic for all of our tests of our analysis. The Fisher's exact test does not have a test statistic. The output for the Fisher's exact test will simply be an exact probability p-value, not a p-value based off of a test statistic. You will still analyze the p-value for Fisher's exact in the same manner you are used to. If the p-value is smaller than your chosen alpha level of significance, you reject the null hypothesis and say that there is an association between the 2 categorical variables. If the p-value is larger than alpha, you accept the null hypothesis and say there is no association between the 2 categorical variables. To report your analysis using a Fisher's exact test, you would state that you performed a Fisher's exact test and provide the p-value. You should also report the effect size as measured using phi. Our final nonparametric test for this lecture, McNemar's test, is used to see if there's a significant change in the proportion of responses for a dichotomous outcome, an outcome where there are 2 options such as yes or no, when measured in the same group of participants at 2 different times, such as before and after a treatment or across treatments. This is like a before and after test for paired data, where you compare the number of changes from yes to no or from no to yes to determine if the changes are due to chance or to the intervention itself. An example of when this test would be used would be if you want to see if nurses feel more prepared for data analysis after a statistics course. You would ask nurses prior to the course if they feel prepared for data analysis, where they have the options of checking yes or no. After the course, you ask them again if they feel prepared and look at how many change their answers from yes to no or from no to yes. McNemar's test has 3 assumptions that must be checked. First, you must have a random sample. Second, you must have exactly 1 categorical dependent variable with exactly 2 categories and 1 categorical independent variable or intervention variable with exactly 2 groups. So in our example, the dependent variable is feeling of preparation, measured as yes or no. The independent variable is the statistics course, with the groups being before taking the course and after taking the course. The third assumption is that the groups for your dependent variable must be mutually exclusive. In other words, nurses can only feel prepared or not feel prepared. They cannot check both yes and no. The null hypothesis for McNemar's test would generally look like there is no difference or change across the 2 associate observations, and the alternate hypothesis would generally look like there is a difference or change across the 2 observations. As with all tests of statistical analysis, you would use software such as Microsoft Excel or IBM SPSS to compute the test statistic and associated p-value. Of interest, the test statistic that the McNemar's test will report is the chi-square test statistic. If the p-value is smaller than our chosen alpha level of significance, we will reject the null hypothesis and say that there is a change across observations. If the p-value is larger than our alpha, we will accept the null hypothesis and say there is no change across observations. To report your analysis using a McNemar's test, you would include the chi-square statistic with its associated degrees of freedom and the p-value. As a reminder, your statistical software will provide degrees of freedom, but in case you were interested in the formula, degrees of freedom is number of rows minus 1 times number of columns minus 1. Furthermore, since your contingency table will always be 2 by 2 for McNemar's test, your degrees of freedom, therefore, will always be 1. You should also report the appropriate measure of effect size. Since the contingency table is 2 by 2, you report the value of phi. By the very nature of the assumptions of parametric tests, anytime we want to analyze categorical data, we need to use a nonparametric test. The nonparametric test we discussed in this lecture did not analyze the rank of the data, as some of the data were at the nominal level of measurement and could not be ranked. Rather, these tests use contingency tables to allow us to analyze the association between 2 or more variables with 2 or more categories each. While chi-square tests can analyze more than 2 categorical variables, you will usually see only 2 variables analyzed in practice, and both Fisher's exact test and McNemar's test only analyze 2 categorical variables. The chi-square test allows us to compare 2 independent categorical variables where each variable has at least 2 categories. It has the most assumptions and requires a large data set and a robust data set where every cell is filled in the contingency table and no more than 20% of cells have a count less than 5. When the assumption of the chi-square test are violated, we can run a Fisher's exact test if the contingency table is exactly 2 by 2. If we want to compare changes in dichotomous answers from before to after an intervention or across exactly 2 interventions, we use a McNemar's test. The measure for effect size of contingency tables of exactly size 2 by 2 is phi. This includes all Fisher's exact tests and McNemar's tests, as well as some chi-squared tests. If the contingency table for chi-square is larger than 2 by 2, we measure effect size using Cramer's V. Because your software will likely provide output from multiple statistical tests and measures of effect size when you analyze categorical data, it is important to know when to choose which test to report and which measure of effect size to include with it.